To start developing some intuition about the second law of thermodynamics and entropy, we're going to work through a short example problem. And so in this example problem, what we're looking at is liquid toluene that's being reversibly heated from 12 degrees Celsius to 55 degrees Celsius at a constant pressure of 1 bar. And so in this process, what we want to determine is the total entropy change of the toluene for two different situations, where in the first situation, our constant pressure heat capacity is going to be equal to a constant, and the second situation, our constant pressure heat capacity is going to be equal to a linear function of temperature. Okay? So what I want you to do is read the problem and kind of think about, how to sketch out this system. Pause the video here to do that. So for this problem, we're asked to solve for the entropy change of the toluene as it's heated from 12 to 55 degrees C. We're not given any amounts, and so what one can do is you could assume a basis of like 1 mole or 1 kilogram. But what we're going to do is when we actually calculate the entropy, we're actually just going to calculate the molar entropy. So it's going to be in units of joules per mole K. All right, so that's just a small kind of tiny thing we're going to do, but it won't really affect our application of the second law of thermodynamics. In any case, so to sketch out our system, what we could do is we could just draw our system box of toluene. So we'll just abbreviate toluene as T. All right, in state 1, our toluene is going to have a pressure of 1 bar and a temperature of 12 degrees Celsius, but we should convert that into absolute units. Okay? And in state 2, the toluene is going to be heated, so there's going to be some sort of differential heat added to the system. And this causes the toluene to heat up to 55 degrees Celsius, or 328 Kelvin. Okay? But the pressure is going to remain the same. All right? And this problem wants us to figure out the change in entropy. Okay? And so for this problem, there's basically two unknowns that we have. The heat that's going into the system and also that change in entropy. So we have two unknowns, and therefore that means we need two equations. Okay? To solve this problem, we're going to make a couple of assumptions. Right. The first assumption is something that's clearly stated in the problem. We're only looking at the reversible heating of the toluene. And so that means that the entropy that's generated in the system, that Sgen, is going to be equal to 0. Okay? The other assumption we're going to make is that at these conditions, at 1 bar and 12 degrees Celsius, toluene is a liquid. We're below the boiling point of toluene. And so because it's a liquid, what we're going to assume is that it's incompressible. Okay? And so because it's incompressible, that means there's not going to be any changes in volume, and that the constant pressure heat capacity is going to be equal to that constant volume heat capacity as well. Okay? We know for liquids and solids that Cp is going to be equal to Cv. Okay? And so these are the assumptions we're going to use. And the next step is to then go through our now 3 different types of balances that we have. So the first balance is our material balance. We have A is equal to I minus O plus G minus C. There's no reaction going on. And also, this is a closed system. Okay? And so that means that the initial moles or mass that we have in the system is also going to be equal to that final amount. Okay? And so the amount of moles in state 1 is going to be equal to the amount of moles in state 2, and we're just going to refer to that as some amount of moles. We weren't given an amount of moles in the problem, but that's fine. um, we'll invoke the fact that the amount of moles is the same in both the state 1 and state 2, and then we'll sort of normalize any entropy values after that. Okay? In any case, our material balance says that the amount of moles is conserved. So now let's go to our energy balance. Okay? So in our energy balance, our du, dek, dep is going to be equal to dq plus dw. Okay? Now, on the left-hand side, one of the other assumptions that we should probably write is that this problem for this system, we're not told anything that would indicate there's any big changes in kinetic or potential energy. So we could say that in assumptions, changes in EK and EP are insignificant. And so that means in our energy balance, we could cancel out the DEK and DEP terms. All right? On the right-hand side, we have DQ plus DW. All right? And there's no kind of shaft work going on in this system. There's nothing flowing. And as far as any sort of mechanical work or changes in the volume, because the liquid is incompressible, we know that dV is equal to 0. So our work term we could cross out. We don't even have to worry about that. Okay? And so what we're left with is that our dq is going to be equal to our d internal energy. All right? And we know from the definition of internal energy that it's related to the constant volume heat capacity. All right? And then based on our the fact that toluene is incompressible, we could say that this constant volume heat capacity is also going to be equal to the constant pressure heat capacity as well. Okay? And so from our energy balance, we now have a relationship between dq and temperature as well. Okay? And so this is important, because now that we have this relationship, what we could do is we could go to our entropy balance now. So SB. And from our entropy balance, we could write out that ds is equal to dq divided by temperature for the reversible case, which is going to be equal to the dq over T of our system plus Sgen. Now for this problem, it's going to be simple because we are specifically looking at reversible heating. Okay? And so, that would allow us to just jump directly to this. But the other thing, because we're dealing with reversible heating, another way to think about it is if we look at the right-hand side of the entropy balance, all we have to do is just cross out the Sgen term. And that's equal to 0. Okay? And so on the right-hand side, we're just left with dq over T. Right? So the point I'm trying to make is this is the same as this. All right? In any case, so we have ds is equal to dq over T. All right? And what we saw in our energy balance is we know that dq is equal to this. So what we could do is actually just plug in the result from the energy balance into our entropy balance. Ncp dt over T. Okay? And so now what we could do is divide both sides by n. Right? We could, since n is a constant, we could bring it inside the differential, and entropy divided by moles is just molar entropy, which is equal to Cp divided by T dt. Okay? Alright, and so now we have a differential equation that's separable. And so at this point, in order to get the delta S, all we need to do is integrate the right-hand side. Alright? But the form of our integral is going to depend on what the functional form of Cp is. Okay? And so let's explore the two different cases. And so in part A, Cp is just equal to a constant, which I'll just call A, right? And that was equal to 148.8 joules per mole K, right? And so what we could do here is if we go back to our entropy balance, we know that Cp is a constant, and so when we integrate both the left and the right hand side, what we'll get is S2 minus S1 is equal to delta S, and that's going to be equal to the integral, or Cp times the integral from T1 to T2 of dt over T. So that's just going to give us the natural log of T2 over T1. Alright, so to calculate delta S, all we have to do is plug in. We know the natural log, and for the entropy balance, we should be using temperature in absolute units, just like in the ideal gas law. Okay? And when we plug everything in, what we get is that the change in entropy is 20.9 joules per mole Kelvin. Okay? And so that's the case for when the constant pressure heat capacity is a constant. Let's now look at the case where the constant pressure heat capacity is not a constant, but instead is a function of temperature. So let's now say Cp is equal to A plus Bt, where A is the same as in the previous part, but B is this coefficient. Okay? And so when we look at our entropy balance, we could plug in this equation for Cp. Okay? So we have A plus Bt times 1 over T dt. And we could factor across the 1 over temperature. And so what we'll get is A over T plus B dt. Okay? And then now, this is still a separable equation, so we can integrate. We get delta S is equal to A natural log of T2 over T1 plus B times T2 minus T1. Okay? And so if we plug and chug into delta S, we have a natural log term that we need to plug into, and just a regular linear term that we also need to plug into. K minus 285. And we see that if the heat capacity is not a constant, but it is instead a function of temperature, our change in entropy is actually a little bit higher than what we got for the constant heat capacity case.